Good morning. It's my pleasure this morning to introduce our keynote speaker and also one of our techs here to get the computers operating.
Side gig, yeah.
Dr. Dave Funk is the Vice President at Nevada National Security Site for the Enhanced Capabilities for Subcritical Experiments portfolio. There's a lot of acronyms because there's a lot of words. In this role, he's responsible for the delivery of new diagnostics to support the nuclear deterrent, including Scorpius, an X-ray radiographic diagnostic testbed, as well as Zeus, a neutron source diagnostic testbed, both to be located in Nevada at the Pulse facility, the Pulse Underground facility. Prior to this job, he spent 33 years at Los Alamos, where he served as project director for the Advanced Sources and Detectors project, which included Scorpius and Zeus, among other things. He was also prior to that, he was a key technical lead for the remediated nitrate salt project. Is that correct?
Yeah.
And then prior to that, he was Weapons Experiment Division lead with around 200 people supporting outdoor firing sites, gas guns, explosive chemistry labs, and the DART hydrotest facility. Dave holds a PhD in physical chemistry from the University of Utah, and he's here today to be our keynote speaker.
Thank you. Thank you, Ralph. Let's see, I'd like to thank Ralph and the Krell Institute for inviting me to give this presentation, and then thank all of you, excuse me, here today, and congratulations. It looks like you got a great program, and so I think you'll have a wonderful couple of days, so thank you very much. I'm going to talk about the Nevada National Security Site, and I want to tell you a little bit about the why that we have it, and then how it's evolved over time and what we're doing today. So we'll kind of go full circle. It was a place that we invented to be able to test nuclear weapons, and it's going to be a place where we've invented to prevent ever testing again. So it's kind of an interesting history from that perspective. I want to thank Gene Christensen and Reed Paderis. They put a lot of this material together. As you heard, I was at Los Alamos for about 33 years, and I've been at the NNSS since November of 22. Just a brief history of nuclear testing. I think everyone remembers that we did the Trinity test in New Mexico, and then we did a series of atmospheric testing out in the Pacific. We'll talk about the needs for an on-continent location. Then there was a brief testing moratorium from 58 to 61, and then a series of treaties actually influenced the testing program and how it evolved. There was a limited test ban treaty, which precluded doing any tests in the atmosphere, space, or water. We got good at containing, but as you'll see, we didn't get perfect at containing these devices. Then the Threshold Test Ban Treaty limited our ability to test in terms of the scale of the devices, and that actually evolved how we actually made the measurements and executed the tests as well. And then in 1992, a testing moratorium existed, and post that, there was the invention of stockpiled stewardship, which you guys hear about today. So the Nevada Proving Grounds was established in 1950. That was its original name. So at the time, we were testing in the South Pacific, but if you can imagine, we had a lot of issues, both with logistics, weather, how do you maintain security? And so there was this top secret project to identify a location in continental United States, and it was codenamed Nutmeg, and determined that the arid Southwest was probably the best place to do that work. And so Truman officially established the Nevada Proving Grounds in December of 1950. Now, it wasn't that long before we did the first shot in the Nevada Proving Grounds. In fact, it was about 5-6 weeks later where we conducted the first test, shot Able. And you can see that this was an above-ground test at that point in time. It wasn't until 1955 that we became as the Nevada Test Site, and there's a lot of people within the DOE complex or within NNSA, especially if they're what I will call old-timers, that still refer to it as NTS. I mean, you hear it pretty commonly as the NTS. The senator from Nevada did not like the fact that it was called NTS, and I'm not going to go into politics here, but we had a name change that occurred as a result of that. So we became the Nevada National Security Site. And we've actually altered our name since then, and I'll talk a little bit about that near the end. We now go by the Nevada National Security Sites. The test site is still the Nevada National Security Site, but we have locations in Albuquerque, Los Alamos, Livermore, Nellis, Andrews, all around the country. And so we actually have a series of sites that support the broader national security mission. The site itself is rather large, 1,360 square miles. It's controlled land, and you can't see it very well, but it's surrounded by about 4,500 square miles of federally controlled land. And so it's in the Nevada Test and Training Range. And it's located about 65 miles northwest of Las Vegas. That's the entrance. If you actually want to go to Pulse, formerly U1A, it's about 25 miles further. P-Tunnel's about 40 miles, so it's actually quite expansive. It's a big location. We conducted 928 atmospheric and underground nuclear tests between 51 and 92. This is a summary of the tests, and you can see in total the number of US nuclear tests is over 1,000. And the number of detonations exceeds 1,100. And the reason why there's a difference is on occasion, a test would actually have multiple detonations simultaneously. And so that's the subtle difference between a test and a detonation. And the other thing to notice on this is, look at the locations. I mean, how many of you knew that we had conducted tests in Alaska, New Mexico, besides Trinity, Colorado, Mississippi, a lot of different places. And so it's kind of fascinating because most people think of the Nevada test site or at Trinity, and that's about it. In '62, it was kind of a transition year for testing. The Limited Test Ban Treaty took place in 1963, but we essentially transitioned from the Pacific all the way to the NTS. And we conducted 54 underground tests. We started to do containment, and I'll talk more about containment and what that means. But we altered our trajectory at that point in time. Okay. There we go. See what happens there. Yeah. So there's an underground test area. You can see this is the site, and if you look, you can see there's a large number of tests that were done in the sort of northeast corner of the site, and then some further north into the northwest. A total of 828 underground tests. About a third of them actually interacted with the water table, and that created some contamination issues within the site. First underground nuclear test was codenamed Uncle. It occurred on November 29, 1951. And I've always found it fascinating that the last test that we conducted is named Divider, because it kind of divides when we did testing from when we don't. And so it's just coincidence, but that is the last test that we had done. There were three basic types, a series that we called Project Plowshare, peaceful uses of nuclear detonation. So some of you guys went out to the site yesterday, correct? And you got to see Sedan Crater, right? Well, Sedan was an example of Project Plowshare. Again, to do excavation, if you will. Horizontal tunnels we use primarily for effects testing, though we tested a lot of different things with horizontal. And vertical holes, we did a lot of work for weapon development, also for stockpile confidence, and then validating designs by the two design laboratories. Plowshare, again, Sedan, so you got to see the crater on the right. One test in particular that I've always found interesting was something called gas buggy. It was a fracturing test, and it worked. And so we released a lot of gas to be able to use, natural gas, right? Problem was it was hot. So, while it worked, it's not something we were going to actually distribute to homes throughout the nation, right? So it's kind of interesting. And then we also talked about underground gas storage. Horizontal tests were executed in something called adits. So a tunnel is a place to walk through, and adit is a horizontal mined area in which you use for debris or some other type of activity. Now, the big advantage of having a tunnel is they were walk-in. It was easy to fill up the space because it was horizontal. You could put a whole bunch more diagnostics, right? You could put a lot of different things because of the space that you had available to it. Big problem with the tunnels was they took anywhere from 2 to 3 years to prepare, and they cost a lot more money. So in 1980s, it was $30 million, which at that time was a significant amount of money. Now, this fun fact was when you fired the device, you also fired the fast-acting closure. So if you think about these experiments we were doing, we wanted to maintain containment, and so we had a fast closure to actually basically prevent any of the material from coming out. And then you can see there's a series of various locations where we could put diagnostics, test chamber. There were stub experiments, and in fact, you know, this is something what would look like at the end of the tunnel when it was ready to go. So you can see there's a lot of equipment. It's actually quite busy, and you can imagine why it took so long to get it ready to go before we did the test. And the other thing is these are one-shot deals, so it's not like you get to try again, right? You know, this was your opportunity to do it, and you got one chance, right, to get data. Vertical tests we did in drilled shafts. We ended up using a crane. In fact, if you were out there yesterday, I don't know, you stopped at Ice Cap, right? Ice Cap was actually in place just prior to the moratorium. And so it's a vertical hole. There's a rack that has the device at the end of it, all the diagnostic cables that come up. And then we would stem it. So we would prevent containment by actually filling it with material. So we would stem the hole to prevent loss of containment. Red shack was known colloquially as the arming and firing shack, so that's how we actually detonated the device. And then there's a series of data trailers that surrounded an area outside the planned subsidence crater, so that actually you would record the data and then the subsidence crater would take place without impacting the trailers. Much faster and cheaper to create. Containment was easier because of the stemming the hole. The experiments were faster, less expensive, but typically you had a much smaller diagnostic suite. So we would only have about 200 cables that we would lower with the experiment as opposed to the 2,000 you could have in a horizontal configuration. Major use was again, and of course you're surprised by this statement, Los Alamos and Livermore use different areas and techniques. Shocking, right? So I think folks know that there's still a bit of a, we're competimates at some level, right? Or we were, or are, if you will. So what it kind of looked like is then you can see the tower on the right-hand side, tower on the left with all the trailers further away in preparation for the test. This issue about containment and doing containment as an evolutionary process. Again, limited test ban treaty, 1963. Prior to that, we tested in the atmosphere. I don't know that we did anything really in space, but underwater and underground, and we said, hey, no more, only underground. The goal was not a single atom out, and then the rule was no effect outside countries. And you can see from the pictures that those were two examples where containment wasn't maintained, okay? And that's not necessarily good, but there was one catastrophic failure, and that was Bainbury in 1970. And in fact, that is the plume from that particular shot, and I don't think anybody could say we contained it. And in fact, the problem was not only did we not contain it, but there were some out-of-country effects. So you remember the rule was nothing out of country, right? And then we had an incident in which we actually created material that escaped our boundaries. As a result, the process became more complex and actually very time-consuming, and as a result, more expensive. There was a test controller that was put in place that was a federal designee. There was a test director that was laboratory, typically designee. And the test controller was responsible for safety and security and making sure everything that we had to do, we could do without ever allowing this to occur again. As a result, the number of tests that we executed were cut in about half. So we were doing, tests pretty often, and you would say, well, why were we doing so many tests to begin with, right? And part of the reason we did a lot of tests was, the very first nuclear devices we kind of understood. If you think about what we had, do you guys remember MANIAC, the computer MANIAC? Anybody remember that? No, okay. So what were computers really back in the 40s? Were they machines or were they people? They were people, right? A computer was actually a person that did the computation. And a lot of what we were doing was starting to understand the physics of these devices, but we were doing it in very much of an Edisonian way. And so, and we'll talk a little bit more about how that's evolved, but when we did a lot of the tests, we were altering design, we were trying out new concepts, we were changing configurations, and all of it was our intention to help understand better and the overall goal of like making them lighter, making them more effective, making them greater reliability. So there's a whole bunch of reasons why we did that and why then the complexity also grew. Now, it got even worse when the limited test ban, or the threshold test ban treaty was put in place, because that limited the yield to about 150 kilotons. Yeah, I know that's like small, right? No, that's actually a very large number, but it actually had an influence on how we did tests. And as a result, we wanted to have more diagnostics, which meant much larger canisters, more shielding, heavier loads, and you can see that's an 84-inch diameter, 120-foot long rack. There was a ton of more recording trailers. We actually had more recording scopes, and then you can see again a couple hundred cables going down with cranes that had 500-ton capacity, right? So you can this is a big deal. In fact, in the heyday, apparently, when you came over CP Hill, you could see lights at night, out in the distance from the holes that were being, worked at the various points in time. And one thing I want to mention about scopes is when we had a lot of scopes, and this even occurred up until '92, now you guys all probably have worked with oscilloscopes, digital scopes, right? You got nice, Keysight, Tektronix, take your pick, digital, beautiful screens. You can plug in well, I'm old, so I used National Instrument GPIB, but you get the point. You can do data transfer out of it. And these days, we use Polaroid film. And so there would actually be a camera that was looking at the phosphorescence from the scope. And it was, literally a cathode ray tube. And we recorded it with that type of process. Now, it's interesting. We still have some of these scopes. They're called Rossi scopes, and we still have them in storage. Now, personally, I'm not quite sure I think there's a lot of value in that, but there is a desire, if we were to ever do a test, to put a Rossi scope along with your fancy Keysight. Okay, just to make sure you got the same result. It's kind of fascinating, but we still have those scopes today. Oh, sorry. So 1992 was when the moratorium happened. And the moratorium is pretty interesting because the reason it happened was it wasn't our own doing at some level. So Gorbachev of the Soviet Union was reacting to a lot of negative press about the environmental and health issues that occurred in Kazakhstan as a result of testing. And so he basically unilaterally declared a moratorium for the Soviet Union. So the US response was to say, hey, we can do that too. So in '92, we actually implemented a moratorium. And you can see that we had this unfinished program, IceCap, Fortune, Greenwater, GABS, and then there was a future program. And Congress said, hey, we're going to do 15, 12, 9, 6, none. And so we've never done any since then. And that moratorium continues through to today. And in fact, there's a Comprehensive Test Ban Treaty which plays a role in this, right? And the US was the first to sign the Comprehensive Test Ban Treaty in '96, but it has never been ratified by the Senate. And so while we abide by it, it is not in force. There are no, it needs, I think, 8 signatories, something like that, to go into place. So, current moratorium, 31 years. You got the Comprehensive Test Ban Treaty. and there's questions about our stockpile. And this was probably real after '92. You know, we'll test bombs for food, because that changed the dynamic. I mean, this was a very interesting place that was invented to do testing. And now we're saying we're no longer going to test. So what does that even mean? So stockpiled stewardship was invented in 1995. And it was invented by a guy named Vic Reese working with the laboratory directors. At the time, Sig Hecker was at Los Alamos, Bruce Tarter was at Livermore, and Paul Robinson was at Sandia. And the whole goal was, how are we going to maintain confidence in our ability to our stockpile without testing? Because a lot of the tests we did, if you saw on one of the slides, we call them stockpile confidence tests, right? And so we actually would build devices, take them in, detonate them in its full configuration. But we're not going to do that anymore. So the idea was to develop a suite of test beds as well as computational capabilities, not people now, machines, right, to actually be able to develop more rigorous models, to compare against the experiments that we conduct at the test beds, and then validate based on our test history, because we still had a lot of data and diagnostics from those tests, to have an overall approach to validating the stockpile and then being able to continue to certify while not testing going forward. And I think you guys know that every year the laboratory directors write a letter that goes to the Nuclear Weapons Council, right, and basically supports that, hey, the stockpile is good to go, or they'll identify any issues or whatever it might be. So this is what became the Stockpile Stewardship Program. I think we have Stockpile Stewardship Fellows, right? So that's how the origin of all of this. Now, a lot of the work that we do is really studying the pre-nuclear phase. Now, that's not entirely true, so let's just talk about the capabilities that we have. So in '95, there was kind of a deal that was struck, right, that each of the laboratories was going to have their capability, aka TOY, right, to be able to help study the stockpile. So Los Alamos had the dual-axis radiographic hydrodynamic test facility. Sandia had Z-Machine, which studies high-energy density material. Livermore has the National Ignition Facility, which studies high-energy density materials. And then here at the site, we didn't have too much at the time. We had Atlas for a little while, but we didn't have a lot. Livermore also had a hydro test facility. It still operates today. It's the Flash X radiograph machine at the confined firing facility. But a lot of our confidence is really the primary, and how does the primary work, and do we have confidence in the primary? Because if we don't have confidence in the primary, then you can't have confidence that the secondary will actually go off, and we have to understand that going forward. So a lot of the work that we do locally now is really emphasizing the pre-nuclear phase. So testing and stockpile stewardship, I think this is just fair. Experimentalists still need data, and we always got to challenge theorists and designers, right? Because that actually is how we improve our capabilities, our understanding. We're always challenging ourselves to improve that. I'm going to talk about subcritical experiments that we conduct. When I say K-effective less than 1, do you guys kind of understand what I'm talking about? If you think of a nuclear power plant, when K-effective is at 1, the number of neutrons being lost is equivalent to the number that are being generated. When K-effective is less than 1, then the fissions will decay away. If they're greater than 1, you're in the explosive or exponential regime. That's how an atomic bomb works, and with high K-effective. So to remain subcritical means to maintain K-effective less than 1. We have a couple of capabilities that I'll touch on. It's a 2-stage gas gun, Jasper, that operates at the site. Pulse, formerly U1A, I'll talk a little bit about. And then we have done some subcritical experiments in holes. So Unicorn was an example of a subcritical experiment that was done in a vertical shaft. Also capabilities that exist across the complex are the firing sites, including DART at Los Alamos, Site 300, which is where CFF FXR is located at Livermore, and additional firing sites. They also have some capabilities at Heath at the main site. And then there's a big explosives experimental facility at the NNSS where we can do very large tests, open air tests with extremely large quantities of explosive. And of course, you have implosion using lasers at the NIF, and then also liners at Z. And so all of this actually provides a lot of data that we can utilize to challenge ourselves, validate that our models work, that they're actually providing the right information, and that we can continue to certify. Effectively, there's something called quantification of margins to uncertainty. So we want to reduce the uncertainty so that our margin to uncertainty is always getting larger. So JASPER stands for Joint Actinide Shock Physics Experimental Research. It's a two-stage light gas gun, can throw projectiles up to about 8 kilometers per second. We use it to study SNM, and so we'll take a projectile, flat plate, and then the target will have various configurations depending on what we're wanting to study. Is it straight equation of state? Is it SPAL? Is it some other types of capabilities? And so the experiments are designed, and then there's a series of diagnostics, pins, fibers, PDV, VISAR, a whole host of laser-based diagnostics. Again, trying to infer pressures. Temperatures are always hard in shock physics. Temperature is extremely hard measurement to make. Don't know why it does that, but it does. Studying high strain rates in these materials, and we look at plutonium and other surrogate materials. The place that I'm, of course, most interested in at this point in time is PULSE. PULSE stands for Principal Underground Laboratory for Subcritical Experimentation. Previously, we all referred to it as UNA Complex. Change is hard. There's a lot of people, you know, if I had $1 for everybody said UNA, I'd probably be pretty rich right at this point in time. Original shaft was mined for an underground test that was canceled in '68. In '88, the shaft was reopened, and then a 1,460-foot horizontal tunnel was mined at about 963 feet below grade. 1990, there was a nuclear test that was conducted at PULSE. It was the Ladue nuclear test. And today we're using the horizontal test tunnels for basically the test beds that I'm going to talk about in the next few slides. In this series of test beds, we do subcritical experimentation. We're focused on plutonium, and we're focused on it in its entire regime from initiation to late time behavior of the implosion. Again, SEEs, K effective less than 1. We want to use special nuclear material. We typically use plutonium, and at PULSE, typically it's going to be plutonium-239. Uranium could be used, but we are focused really on plutonium. At early implosion, there's a lot of things that we've already been able to do using JASPER. I'll talk about the Cygnus test bed in a minute. But a lot of our interest is the equation of state, strength, SPAL, damage, any ejecta that gets created from a shock wave interacting with the metal and its free surface. Of course, we want to understand criticality, the formation of the cavity, and the overall impact on boost. So data that we've gathered to date, just with the one capability that we have in place, has influenced our stockpile, and we've made changes as a result of the data that we've gathered. So this is not trivial. This is actually extremely important in terms of how we basically understand and then assess our stockpile going forward. Now, in 2014, there was a mission need that was established for the enhanced capabilities for subcritical experiments. And when I say nuclear performance depends on the way plutonium implodes, it's really the hydrodynamics of plutonium, right? That's what we're studying. It's all about the hydrodynamics. So the HE will detonate, and you'll get early time behavior of the implosion, but it's this late time behavior that we don't have a lot of data on. And so if you think about it, you get very high pressures and temperatures, and the material behaves differently. So hydrodynamics means flows like water, right? However, these materials have strength, They're still solids, even though they flow like water. And so that behavior and then understanding the EOS and its behavior at late time is critical for comparing to our models and to validating the underlying physics so that we can certify in the absence of testing. There's two primary capabilities that we're developing as part of this mission need. The first capability is a radiographic capability. That's the Scorpius machine, and I'll talk a little bit more about that. And then the other is the Zeus machine, which is a DPF that generates neutrons. So there's a whole portfolio that we're executing to support the ECSC mission need. First is the UNA Complex Enhancements Project. No, we're not going to change it to the Pulse Complex Enhancements Project. It's too late for that, right? But it's a total, think of it as the civil or the infrastructure for this new accelerator, the Scorpius accelerator. It's about $825 million of scope. Next up is the R&D that we've been doing for NDSE, so neutron diagnosed subcritical experiments. I'll talk a little bit more about them in a minute, but at bottom line, what are they? It's you take a device near critical, you impart a burst of neutrons that creates a fission chain, and you monitor that decaying fission chain. There's a Zeus testbed facility infrastructure, so equivalent to USEP. There's the civil for the Zeus machine, and so we're doing both of those in the underground. We did an entombment drift both for Zeus and for Scorpius. You don't capitalize an entombment drift. What's an entombment drift? I do an experiment in a vessel, I put the vessel at the back of the drift, I grout it in place, and I kind of walk away. And you use up that volume, so it's not capitalized equipment of any type. And then, of course, there's the ASD, the Scorpius machine. It's a major item of equipment. It's a $1.8 billion linear accelerator. And we'll talk more about that in the next couple of slides. But overall, if you look at the total set of capabilities, there's going to be a new access, there's new buildings on the surface. We're spending nominally about $3 billion for these new capabilities. Now, it sounds like a lot of money, but then I think about Savannah River, and I think not so much. But this is a significant investment in our nation for these capabilities at the site. In the end, we'll have 3 test beds. There's a small scale for fundamental and focused experiments. It's 2 pulses, Cygnus at 2.2 MeV. We'll have this large scale capability, the Zeus test bed in the UNA.03, and then the large scale Scorpius. And again, we'll be able to characterize essentially plutonium almost through its full range of an implosion, from the early time behavior, which we capture with Cygnus, to the late time behavior that we capture with Zeus and Scorpius. So Cygnus is a set of rod pinch diodes. It's 2.2 MeV, about 5 rad. You can't look through significant quantities of plutonium with this capability. It's great for looking at ejecta, it's great for looking at sort of shatterography, things like that, but it doesn't have the penetrating power to be able to really look through implosions, particularly at late time. And in fact, as we'll see, the reason why you end up going to much higher energy with Scorpius is so that you generate photons that are in the 3 to 5 MeV range. We do experiments in the relevant geometries and scales. What you can see is the blue devices, they each have 3 cell, or the 2 rod pinch machines. They come up to a containment barrier. That's what's kind of in orange or brownish. And then you see the vessel. That's a 3-foot diameter vessel in which the object is, the explosives are initiated. In that 3-foot vessel, then we capture the data using X-rays passing through, and then a whole host of diagnostics, BLR, MPDV, PDV, VISAR, et cetera. Now, ECSC, Cygnus is existing. It's been doing experiments for a long time. In fact, that machine was originally going to be used for 1 experiment, and I think it's done like 33, and it's got well over 5,000 shots now. It's got close to 6,000 shots. ECSC then is really USEP, ASD, and then ZTBFI and NDSE. If you look at the underground layout. This is a plan view of the underground and its current configuration. You can see that the Scorpius accelerator is going to be in that top. That's called the 104 drift. The drift that's to the left, that's in yellow, is a back door that was created to be able to move all of the machine to that 104 drift. Now, the other thing we had to think about was making sure that all the material could come down the hoist. This is 963 feet below grade. So it's something where we come in modular components and then assemble the modular components to make the entire machine. And so all of that was thought of as we planned and designed this machine. Drift on the furthest left, that's yellow, is the entombment drift. It's designed to be able to hold 2 6-foot vessels now for experiments for 30 years, so a total of 60 experiments. We use 6 foot because you can actually use greater quantities of explosive, and you have different scales that you can use in that configuration. Okay, ASD, Advanced Sources and Detectors. We're going to be using Scorpius. So Scorpius is unique in that there's a capability at DART. It's the Axis 2. So there's 2 electron accelerators at DART. One is really a long pulse accelerator. In fact, it's Axis 2. We take multiple images with it, and we do that by chopping the beam. So the beam is essentially directed into a dump, and then we kick part of it out to a target, and then we can do that up to 4 times today. Actually, will soon be 8. But those 4 electron pulses interact with the target. As they slow, they create something called Bremsstrahlung radiation. So the electron slowing down will stopping radiation. And those X-rays have essentially start at the end point. So if it was a 20 MeV machine, you'd have X-rays from 20 MeV, but they also downscatter, and you end up with a lot of photons in the 3 to 5 MeV range. That's very interesting to us because plutonium has essentially a window in 3 to 5 MeV. And so that's the useful photons typically for these kinds of experiments. Then you can look through quantities of the material. This is a multi-partner collaboration. Los Alamos is the lead lab. They have responsibility for the accelerator, the downstream tech transport. Now the detector is really managed by NNSS. But originally it was a Los Alamos scope. The injector is a collaboration between Sandia and Livermore. Sandia has primary responsibility for the injector, the cells, the push-pull, the configuration. But interestingly enough, not the pulse power. What's Sandia known for? Pulse power. But there is a capability that was invented at Livermore. It's called a solid-state pulse power. Actually was first used on DART for the kicker. So the kicker I talked about to create the pulse of electrons, that was used at DART using solid-state pulse power. Scorpius is driven by 984 solid-state pulsars, each capable of 25 kV, each has 45 boards. All of them are independently triggerable, and you can actually tune the pulse and tune the energy, and yes, we'll take advantage of ML, AI to actually be able to tune this machine. So the collaboration, again, the injector is where the electrons are born, and then move forward, get accelerated in 102 cells. Total energy is 22.1 MeV, and it's 1.4 K-amp. So unlike a lot of photon machines, which are micro or milliamp, we throw kiloamps of electrons to create the X-rays required to be able to look through these devices. Okay, Zeus, NDSE, it's a modern technique to measure dynamic reactivity. I kind of already touched on this. Zeus is a new test bed. It will use a dense plasma focus that is currently operational in Area 11 at the site. It essentially creates a Z-pinch. It's coaxial. Actually, I'm going to show a movie, and you'll get to see how Zeus works. So we'll take a look at a movie in just a second. Bottom line is we use that strong neutron source to initiate this decaying fission chain, and we measure that decaying fission chain. And I don't need to talk about it because I want to show you now.
Underground at the Nevada National Security Site, The U1A complex is the prime location to conduct subcritical experiments. Coming online is the Zeus testbed, which will enable large-scale subcritical experiments. One of the key diagnostics that the Zeus testbed will house is the Neutron Diagnosed Subcritical Experiment, or NDSE. This new diagnostic tool supports the ability to make prompt reactivity measurements of the dynamic experiment. This enables us, for the first time since the cessation of underground testing, to assess the nuclear performance of a given system. Key components of the NDSE system are the pulsed neutron generator, the collimation elements, the gamma detector array, and the recording system. The pulsed neutron source that enables the NDSE diagnostic is the Zeus Dense Plasma Focus, or DPF. To prepare the system for firing, capacitors are charged to a specific voltage and then discharged at a precise time during the experiment. Once the trigger signal arrives at the DPF generator, a plasma sheath is formed within the vacuum chamber. Magnetic forces then push the plasma sheath up and ultimately inward onto the DPF anode. As the sheath collides with itself, it compresses the deuterium-tritium fuel, causing nuclear fusion. The fusion reaction creates an intense burst of high-energy neutrons. While the 14 MeV neutrons are emitted in all directions, only the collimated neutrons, shown here, pass through the collimation and shielding elements. The interactions of the high-energy neutrons with the fissile material generate both neutrons and gamma-ray scattered particles. The collimation elements narrow the beam, allowing only select gamma rays to travel towards the detector array. The collimated gamma rays, now traveling at the speed of light, are followed closely by the slower-moving neutrons. Once the high-energy gamma rays reach the detector array, they are converted to light photons within the scintillating element. These light photons are amplified and converted to an electrical signal and transmitted to the recording system. Soon after, the slower-traveling neutrons impact the detector wall and impart energy into the scintillating elements as well. Once this happens, the window for the NDSE measurement has now closed. The data is collected and then analyzed. The resulting slope of the recorded signal is a direct measurement of the reactivity of the system. A slope closer to 1 indicates higher peak reactivity for subcritical systems. The data collected through the NDSE measurement technique will aid in the assessment of the nation's aging nuclear stockpile.
Yeah, so that's a little bit about Zeus, and as you can see, like I said, that machine is up and operational in Area 11. We're going to be doing a series of tests with it over the next month, looking at another SNM article to evaluate signal to noise. So bottom line, SCEs are going to provide a lot of data on plutonium. We're going to have a couple of capabilities. This will close the gap that was identified when CD0 emission need was established in 2014, and we'll have two capabilities, both the ASD capability, which will provide X-radiographs, so think of it as the density profile of the object, and then the Zeus capability, which will provide the dynamic criticality measurement. Now, one thing I wanted to mention is that long run, Scorpius itself can be used to create a decaying fission chain. And we don't have the detectors quite at the right technology readiness level. But if you think about it, the photons are greater than 10 MeV. They will fission the nuclei. You'll start a chain reaction, and that chain reaction can be observed to look at how critical that object was as well. So the long-term plan is to have the ability to make density measurements simultaneously with criticality measurements on the Scorpius machine. Now, I wanted to do another video because I gave you a sense of NNSS and what we're doing. So you kind of got a sense of ECSC, how we went from, hey, the site is all about testing, to, yeah, we're about testing, but not nuclear explosive testing. Now we're about testing in a subcritical regime. But the site also evolved in terms of its mission set. And so I didn't want to, short shrift to the folks that do a lot of other things besides what I wanted to talk about. And so this is a video that kind of gives you a little bit broader perspective of the site itself.
The foundation of the well-being and survival of the American military and the defense of the nation are underwritten by our nuclear deterrent. The responsibility for certifying the nation's nuclear weapons stockpile is safe, secure, and reliable falls upon the National Nuclear Security Administration. Every year, the NNSA provides a report to Congress and the American public. The NNSA faces the challenge of certifying the reliability and safety of the United States nuclear stockpile without nuclear testing. The Nevada National Security Sites, a group of proud professionals and places stretching from coast to coast, everyone working together toward a vital nationwide, even worldwide goal: we secure America's future. Anchoring this group of people and places, the Nevada National Security Site itself, at over 1,300 square miles. The site is on federal land, surrounded by federal land. Very large, very remote, very safe, very secure. The NNSS is host to a stunning array of research. Like what? Like PULSE. It used to be called U1A, now Principal Underground Lab for Subcritical Experimentation, or PULSE. Nearly 1,000 feet underground, PULSE is the perfect place for high security and high hazard experiments and research involving nuclear stockpile readiness. It's vital to understand every millisecond of nuclear processes, especially when certifying the reliability of America's aging existing weapons. Construction is currently underway on new test beds, a signature investment in the PULSE Underground Laboratory that will be home to the Advanced Sources and Detectors Scorpius machine and the Neutron Diagnosed Subcritical Experiments machine named Zeus. Scorpius and Zeus will enable subcritical experiments that image special nuclear material during multiple stages of detonation, yielding essential data on stockpile safety and certification without reaching critical mass. The new scientific instruments will also enable the NNSS to offer federal and private partners 3 parallel operational testbeds for new and enhanced subcritical experiment capabilities. While PULSE is below the surface, above the surface is another part of the site, Port Gaston. The NNSS controls the airspace above the site. At Port Gaston, experiments involving rockets, drones, and other aircraft are possible. Port Gaston also hosts experiments and research into anti-drone technology. Non-proliferation of nuclear weapons is vital to the interest of the United States. Special experiments in places like P-Tunnel study conventional explosions, seismic waves, and other reactions in different geologic formations and other conditions. These experiments will help us know who is testing nuclear weapons. In a small valley on the site, JASPER is an acronym for Joint Actinide Shock Physics Experimental Research. This facility showcases a 2-stage gas gun used to propel a pellet at a target at unbelievably high speeds, up to 17,000 miles per hour. The collision is observed, photographed, and has thousands of data points recorded, all in microseconds. The JASPER gun mimics temperatures, pressures, and strain rates of materials similar to those in a nuclear weapon. The NNSS is home to Counterterrorism Operations Support, or CTOS. Homeland Security is the mission priority here. Our people use realistic training with real radioactive material to help first responders quickly and safely react to radiological incidents. Training is offered at the site, or instructors and equipment are taken to the first responders so they can learn in their own communities.
Another mission puts NNSS assets in the air. Helicopters and planes based in Nevada and Washington, D.C., regularly fly over major events across the country. These aircraft and people are from the NNSS Remote Sensing Laboratory. These people are the best in the world at finding dirty bombs or other radiological sources. Their aircraft are specially designed and equipped to discover these types of threats. The Special Technologies Lab, or STL, in Santa Barbara, California, is well known and highly respected by our nation's national security enterprise for innovative ideas and quickly finding solutions to complex challenges in support of stockpile stewardship and other vital national security priorities. The NNSS never stands still. At the NNSS, our mission takes us everywhere. Everything we do protects liberty and freedom in America and around the world. The NNSS, we secure America's future.
Yeah, still had stuff on Zeus and Scorpius. Sorry about that. But anyways, and then any questions? I know I ran a little long. Apologies. Anybody have any? Is that okay if I take one? Yeah.